Good morning. We will continue with what we were doing with nozzle area ratio. I replotted the figure which we had in the last class. We had one case, we had the under expanded nozzle. In other words, the exit pressure here was lower than the was higher than the ambient pressure, so that the flow continues to expand. How does the flow expand? When it meets outer, you have a series of rarefaction fans, and when these rarefaction fans hit the boundary, they are reflected as oblique shock waves, and these oblique shock waves, when they interact with the boundary, I get rarefaction fans which again form oblique shock waves, and this trend continues. Therefore, when I look at an under expanded jet, as it were, I start with a high value of PE. I get first a set of expansion fans which are followed by a oblique shock wave, and behind the oblique shock wave, since I have higher compression, I get something like a higher temperature, and this higher temperature region shows up as light. Anything which is at a higher temperature emits more light, and this is seen as luminous zone. And this again I have rarefaction fan, again compression fan, again I will have another luminous zone over here. Similarly, if I have an overexpanded nozzle, the value of pressure at the exit is lower in this case than the ambient pressure. Therefore, I form something like a shock wave which matches the pressure, and therefore, to be able to get the value of PE equal to PA, I have something like an oblique shock wave, and these oblique shock waves, they continue to interact, and I have now something like an oblique shock wave. But after the oblique shock wave, because I need to have the velocity at the center which is still going straight, and therefore here the pressure exceeds the ambient pressure, and then I have another expansion, another high pressure region, and therefore in this particular zone I have something like a high temperature region, or high pressure high temperature region, and high pressure high temperature region gives me some light. Therefore, what is happening in an under expanded nozzle, I have a set of initial rarefaction fans followed by oblique shock wave. In the case of over expanded nozzle, I have oblique shock waves which thereafter result in the expansion fan. Therefore, there is a distinct change in the plume if I consider a rocket moving up. If the expansion is not there, maybe I should get some bright spots, and these bright spots are due to the shock wave, and these are known as shock diamond. I get this both for the under expanded flow as well as the over expanded flow. The only thing is that there is a phase difference. If I have over expanded flow, the shock diamond comes much earlier, because I do not initially get the expansion fan, I start with the oblique shock wave, it happens much nearer, whereas if I have under expanded nozzle, it is shifted out a little later. Therefore, a trained eye, if I look at a nozzle, and that is where I will again show those two pictures which we had earlier. Yes, see, in this case we had the nozzle, we had the oblique shock wave, we would have got some shock diamonds a little later as is shown here, but in this particular test some cooling of the plume was done, therefore it is not visible. This is a test wherein you have the exhaust of the nozzle, and you have one shock diamond, shock diamond, shock diamond, and it keeps on going. In an inviscid flow you could have infinite number of these diamonds, but with the viscosity there is some dissipation, and that is where I showed this particular slide which shows this flight SR 71, in which case maybe you do see over here from the exhaust you have one shock diamond, second one, third one, fourth one, and keep on going. The other engine keeps on producing this. Therefore, the shock diamonds are a reflection of under expansion and over expansion in a nozzle. It is very nice to see some of these pictures and try to conjecture what is really happening. Therefore, but in practice there is another problem we have. Whenever I have these oblique shocks, when the oblique shocks interact, very often you get something like a mark shock, a stem shock is formed, and I have, instead of having a regular reflection like this, I have a mark reflection, and therefore a shock is formed like this. Therefore, this shock wave is known as a mark shock wave. That means I have an incident shock, I have a reflected shock, I have a strong shock over here. Similarly, I have the incident shock over here, reflected shock, and so on. This the shock pattern therefore continually changes, and you have a shock structure forming over here. Similarly, I will have something like a shock structure which is getting formed like this. That is, the simplified picture gets little complicated because I have something like a mark stem shock which is formed, and that is how you see the diamonds in those particular pictures. The diamond pattern is actually something like this. Therefore, this is how the pattern looks like. Normally, I would have expected maybe incident waves like this. What we said was the diamond pattern is something like this, and then you have the reflected shock which goes, but very often you have a mark stem shock, and I do not observe this reflection pattern over here. I will have a shock like this, and then it gives rise to the reflection over here, and I get a diamond over here, and this is what is there. Anyway, this is of interest to see that whenever I have a expansion of a nozzle, the expansion could either be under expanded, or it could be over expanded, or it could also be something like an optimum expansion, right. Optimum is when the exit pressure of the nozzle is equal to ambient pressure, in which case it goes straight as it will. See, there are some problems we have with under expanded and over expanded, and we told ourselves, when supposing I were to have a rocket nozzle with, let us say, an area ratio of, let us say, around 10 or so, which gives an exit pressure, let us say, equal to the ambient pressure on the ground, and if this particular nozzle were to fly at an altitude wherein PA is at a high altitude less than the value on the ground, let us say PA on the ground, then what is going to happen? My exit pressure has reduced, the nozzle becomes under expanded, and therefore, I will not be able to get a high value of Vj, which would have been possible had I got a high value of expansion ratio. Whereas on the other hand, if I have a nozzle on the ground, I have a area ratio of, let us say, 40, which gives me an exit pressure which is less than the ambient pressure on the ground, because now the nozzle is over expanded. Then in this case I will have flow separation, which is again not desirable, because I have shocks and I have asymmetric flow separation, or I have side loads on the nozzle. Therefore, we find that in general we cannot always have, we cannot live with under expansion because I lose jet velocity, but at the same time I need to have, I cannot have over expansion because I cannot deal with flow separation also. Therefore, there are some problems in nozzles, and therefore, let us tell ourselves, supposing I have, let us say, a booster stage of a rocket, and we define booster stage as a ground stage which has to fly, let us say, between 0 kilometers to something like, let us say, up to 40 kilometers or so, then I cannot have a nozzle which will be perfect or optimum for all these conditions. In other words, at 0 kilometers I have 100 kilopascal pressure, at 40 to 50 kilometers maybe my pressure may be something like maybe 4 or 5 kilopascal, right, might be lower. Therefore, my ambient pressure is decreasing, and therefore, it is not right for me I cannot have a single nozzle, I cannot have a rocket with a single value of epsilon or expansion ratio which will fly throughout this altitude. Therefore, I make the nozzle such that for an intermediate altitude, let us say between these two, maybe I have to fly to 40 kilometers, I design my nozzle for 110 kilometer altitude, in which case the pressure may be somewhat different from 100 and 4, maybe it is something like nearer to let us say 30 kPa. That means my exit pressure of the nozzle, my area ratio is such that the exit pressure of the nozzle gives me a value PE, a value of 30 kPa. Now, this particular nozzle, when the rocket takes off, what will happen? Is it over expanded, under expanded? Exactly. Now, let us just now plot it, plot the figure over here. I have the altitude, and we say this, the design altitude is 10 kilometers. The rocket has to operate up to an altitude let us say of 50 kilometers. This is where I have the optimum nozzle. Therefore, initially the nozzle performs in an over expanded mode, and thereafter it performs in an under expanded mode. By having the rocket perform in an under expanded mode, I am not getting the high value of jet velocity which I could have got. Instead of choosing a value of epsilon which gives me 10 kilometer, had I chosen a value of epsilon which was corresponding to 50 kilometers, I would have got a much higher Vj. Therefore, I am not getting that high Vj, but then I cannot also afford to over expand my nozzle and get into some side thrust problems, and it is always that a given nozzle operates either in an under expanded mode or over expanded mode, but we try to decrease it, and as you would have seen in the earlier figures what I shown, a booster stage has a small nozzle, whereas if it is the rocket is going to fire at high altitude, I will design it with a larger nozzle such that it is more, that is the optimum shifts to the higher altitude, and this is something which we have to keep in mind. I think something more we must remember in while we are talking of under expanded and over expanded nozzles. We told ourselves the nozzle over expands, that means we tell that PE is less than the value of PA, right. This is the condition, but in general gas is flowing at high velocity in the nozzle in the divergent, and therefore you have lot of this inertial forces as it were, and in practice when I have the exit pressure is equal to something like 0.4 times the ambient pressure, then only I have this problem of flow separation and shock formation. Even though ideally I said that PE and ambient pressure, in practice experiments have shown because of the inertial or the forces which are already available, the rocket nozzle can operate at a much lower value of PE compared to PA, and this value is 0.4 times, and this condition was devised by Summerfield and it is known as Summerfield criterion. What is the implication of this? Supposing I have to make a nozzle perform on the ground, that means I have something like a nozzle. Let us now plot the shape of the nozzle, convergent followed by divergent. Then my ambient pressure is equal to let us say 100 kilopascal on the ground. Then I do not need to have the nozzle, the exit pressure, that is the area ratio, such that the exit pressure is equal to 100 kPa, but it is sufficient for me. I can have give a much larger nozzle such that the exit pressure is equal to much lower as 40 kPa, and this is based on experiments because you find that the initial inertial field helps to delay the flow separation process. Having said that, it is also necessary that this is also not perfectly right. In fact, the local Mach number at the zone of flow separation affects it, and the value is in fact given by the value of P by Pa is equal to something like 1.88 into the Mach number at the plane of exit or wherever you want flow separation to the power minus 0.64. In fact, based on experiments, it is not only the inertial force which delays it to a constant value of 0.4 times the ambient pressure, but it depends on the local Mach number at which flow separation takes place, and this is the value of the exit pressure for which flow separation takes place. This is again based on experiments. Therefore, I hope by now we get a feel of for a nozzle. We find that the nozzle area ratio depends on the ambient pressure. Ambient pressure keeps varying in the flight, and therefore we need variable area ratio nozzles. The moment we talk of variable area ratio nozzles, it is also necessary for us to consider the problem of under expansion and over expansion. By under expansion we lose performance, by over expansion we get side loads which are harmful. Having seen that, let us go to the next phase, wherein we also would like to know a little bit more about what is the thrust or what is the force generated by the rocket. What is it we have considered so far? We considered the jet velocity as a function of the chamber properties. We said a convergent divergent nozzle is required. We looked at the area ratio AE by AT of the nozzle. We talked in terms of the under expanded, over expanded and optimum nozzles. By now we are clear about this, but now the question is, what is the thrust generated by a nozzle? What is the thrust generated? You have momentum thrust m dot into Vj. But we were telling ourselves each time that depending on the nozzle area ratio, the exit pressure Pe could be different from the ambient pressure Pa. Therefore, the thrust could come from pressure also, because I am not able to fully expand this. Therefore, I have some pressure also coming. Therefore, let us write the expression for the force or the force developed by a rocket, which we know is equal to rate of change of momentum. Let us put the diagram down. We again start from basics. Let us imagine I have a rocket here, I have a nozzle here. Let the nozzle exit pressure be Pe. Now, what I do is I want to find out what is the force is generated. Therefore, I clamp the rocket on the ground and I attach it to a fixture over here. I hold it on such that I hold it on with a force F such that the rocket is stationary. No, because I want to find out the force which a rocket develops, because my exit pressure is not balanced by the ambient pressure, and therefore I keep this rocket in a position like this. Then I make a control volume diagram about this. Now, I want to find out this force. I find that everywhere on the walls of the control diagram, that is this imaginary lines what I am drawing now, let us call it as AB line, BC line, CD line. The nozzle is EF over here. I find all along this the pressures are the same, and maybe pressure is acting over here, ambient pressure is acting over here. Similarly, ambient pressure Pa is acting over here. ambient pressure P is also acting in this stretch, it is also acting in this stretch over here. Therefore, the only place where I have a difference in pressure is in this region. That means, sorry about this, over this particular area I have ambient pressure PA acting, over here PE is acting. Now, let us write the force equation for this system over here. I get force, or I have a momentum which is coming. What is the momentum? What do I get? M dot n Vj is the momentum thrust, whatever I am getting, and that is balanced by the value of force plus Pa minus Pe over, if I say that the area ratio or the exit area is Ae into Ae over here. Pa minus Pe, this is the unbalanced force in the axial direction, because in all other cases this pressure balances this pressure balances this part over here, this part balances this, and therefore only over Ae I have an unbalanced pressure Pe into Ae in this direction, Pa into Ae in this direction. Therefore, this force, or rather I get the net thrust is equal to m dot into Vj plus Pe minus Pa into the exit area. Therefore, now I have slightly modified my force or the thrust equation, which originally we considered the exit pressure to be same as Pa, and we got an expression as F is equal to m dot Vj. Now, we tell ourselves, well, I have to add the pressure term Pe minus Pa into the value of the exit area. Well, I want to get the force or the thrust developed by a rocket, therefore, I need the expression for m dot Vj we have already derived. We told ourselves 2 gamma gamma minus 1 RTC into 1 minus P by Pc to the power gamma minus 1. Therefore, if I can derive an expression for m dot, I can find out the force which a rocket develops. Let us do that. Now, I can be a little fast, because we have been doing these things for the last 3 or 4 classes. M dot is equal to rho T Vt into At, and it is better I use the reference as At, because that is very standard, that is the throat, and whatever be it I need a throat. Therefore, now I say Vt, and Vt is equal to Vj rho T, no, Vt is equal to At, sound speed at the divided by into At over here. Now, can I now simplify it? Can I write it in a form which is easy to do? Let's do that. I have rho T by rho C into rho C into At into the throat area, this sound speed. Now, I have rho T by rho C, and rho T by rho C we already know is equal to 2 over gamma plus 1 divided by 1 over gamma minus 1. All right. No, please let's keep track. In the last class we derived the expression for rho T by rho C, Pt by Pc and Tt by Tc, and we got this expression. Now, what is rho C? Pc by Rtc. What is At? Sound speed under root gamma R Tt local condition and At over here. Therefore, what does this expression translate to? Therefore, m dot, the mass flow rate, is equal to 2 over gamma plus 1 to the power 1 over gamma minus 1 Pc. I take At over here together Now I have 1 over RTC into under root gamma somewhere here, let us put it, into under root R T T. Now I find I have T T here, T C here, but this is fully here. Supposing I were to get a value here, supposing I were to say I multiply this one by T C and T C here, the expression is still the same. And now if I were to use this, what is it I get? I get now under root gamma into 2 over gamma plus 1 divided by 1 over gamma minus 1 into PCAT into 1 over under root RTC into the value of under root TT by TC. Have I missed out anything? I take RTC under root outside and this gives me under root RTC. I am left with TT by TC here and the remaining things are the same. Is it all right? If I were to simplify this term, I keep this term as it is. Now instead of TT by TC, I can write it as 2 over gamma plus 1 to the power half Tt by Tc is 2 over gamma plus 1 and it was under root, and now I want to combine the whole thing. I tell this is equal to under root gamma into 2 over gamma plus 1 to the power 1 over gamma minus 1 plus half, this is equal to gamma plus 1, that is 1 over gamma minus 1 plus half 2 plus gamma minus 1, gamma plus 1 divided by 2 into gamma minus 1 into 1 over RTC under root is what I get into PCAT, and this gives me, this is all a function of gamma. Let me define under root gamma into 2 over gamma plus 1 to the power gamma plus 1 divided by 2 gamma minus 1 as capital Gamma is equal to under root gamma divided by 2 into gamma plus 1 divided by gamma plus 1 divided by 2 gamma minus 1 excuse me, in which case the value of capital Gamma becomes, or in terms of capital Gamma, m dot is equal to capital Gamma divided by under root RTC into PCAT. This gives me my net flow rate, mass flow rate. Is it all right? Now let us find out what is the mass flow rate through the nozzle. You find that for a given mass flow rate in kilograms per second, if I were to use this expression as something which transfers the mass flow rate into chamber pressure, I get something like, this is something like a transfer function. What do you mean by transfer function? I get, if I were to rearrange this equation, I get Pc is equal to m dot divided by At, that is mass flux through the throat, into 1 over gamma by RTC under root, or rather RTC divided by gamma, I take it upstairs, I can write this as for a given mass flux through the nozzle, this represents something like a transfer function which will give me the chamber pressure. That means RTC by gamma is something like a function which converts the mass flux into pressure. And what is the value? Let us see the unit of under root RTC. What is the unit of RTC? Joule per kilogram Kelvin into Kelvin under root. Joule is Newton meter and Newton meter is equal to kilogram meter per second square into meter, Kelvin gets cancelled, therefore you have meter per second. Therefore you find that the value of 1 over gamma under root RTC, gamma is just a function of gamma, has units of velocity meter per second, and this particular value under root RTC by gamma is what is spoken of as characteristic velocity. It is unit of, therefore I can now write my value of m dot is equal to, from that expression I get m dot is equal to PCAT 1 over C star, where C star I define as a characteristic velocity which is equal to under root RTC by capital gamma. What did I do? M dot is equal to PCAT into divided by the value of R under root RTC by gamma, where this has unit of velocity and therefore I call it as characteristic velocity. Is it all right? We are just defining something because you find that the unit is velocity, and therefore given a rocket, let us say I have a rocket chamber, I am told that the throat area is so much AT, and if I know that the mass flow through the nozzle is so many kilograms per second, I can go back using this transfer function, find out what is the value of chamber pressure. Something like a transfer function which we call as characteristic velocity. It is an extremely important parameter to characterize the mass generation rate of a propellant. We will come back to this. Therefore, what is it we ended up doing? We wanted to find out the value of m dot, and the value of m dot we said was equal to, let us put it down, I have the value there, and therefore I can write now my force is equal to, let us write it out, let us substitute the value of gamma under root gamma 2 over gamma plus 1 divided by gamma plus 1 divided by 2 into gamma minus 1 into divided by under root RTC into PCAT plus PE minus PA into AE. This is the force generated. A is the exit area, which is a suffix E. Is it all right? Let us simplify that expression and get a value for the thrust generated by a rocket. For F is equal to under root gamma, again we have to take it till we are totally done with it, 2 over gamma plus 1 PCAT. Where did Vj go? Vj is here. What is Vj equal to? To gamma RT, all right, divided by, no, something has been lost in the mass itself. RTC has forgotten. No, please correct me. Let us first find out what is the value of m dot. M dot is equal to under root gamma 2 over gamma plus 1 divided by 2 gamma minus 1 PCAT by under root RTC. This is m dot. What is the value of Vj? Vj is equal to under root 2 gamma RT divided by gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 divided by gamma, and now you have plus P minus Pa divided by Ae. Therefore, now if I take PC80 outside and I simplify this whole expression again, can I cut off some numbers? I get RTC over here, and this was equal to 2R chamber temperature Tc over here. Therefore, R and R goes cancelled, and therefore my expression for the thrust is equal to PC 80 into, now I look at these numbers, I still carry under root gamma 2 over gamma plus 1 TC80 is taken outside, RTC is gone, I still have under root of 2 gamma by gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma, plus now I divided, I have Pe by Pc minus Pa by Pc to Ae by At is epsilon, area ratio Ae by At. No, let us try to follow it, because we must understand each term properly. And this whole term, what I have here, I denote it by a coefficient Cf, and I say that the force generated by a rocket or thrust generated is equal to Cf into chamber pressure into At, where Cf is under root gamma 2 over gamma plus 1 into under root 2 gamma gamma minus 1 to the power half into 1 minus this is the expression what I get. Let us therefore write out the final expression for Cf. I think we should not write it again and again, I think we know what it consists of. I want to find out what will be the expression if we have Pe is equal to Pc for an optimum. The value of Cf, that is Pe is equal to Pa optimum, then in this case this goes to 0, and in fact when, let us compare these two terms first. What will happen is, when the ambient pressure is equal to the exit pressure, this term knocks out, but then you are increasing the value of Pa, and therefore the value of Cf corresponding to the value of Pe is equal to Pa will be maximum, and that is denoted by Cf0, or rather I write Cf0 which corresponds to the optimum compared to Cf, I write it as Cf0, or let us put it Cf0 here, is equal to, I just write the whole expression other than this particular term which goes to 0, and I get Cf0 is equal to under root gamma 2 over gamma plus 1 divided by 2 gamma minus 1 into, I have the value of under root 2 gamma gamma minus 1 into 1 minus P by. Whereas if I have something like the exit pressure not being equal to the ambient pressure, if I have something like an over expanded nozzle, I get a negative term. If I have excuse me, optimum expansion in which Pa is equal to Pa, this becomes 0. If I have an under expanded nozzle, I have positive thrust, and in all cases when Pe is equal to Pa, I get the maximum thrust F, because in one case what is happening is the contribution from this increases, but the contribution from this decreases, and only under the condition Cf is equal to Cf0 I get the maximum thrust. That means an adapted nozzle always gives me maximum thrust, otherwise because of under expansion I lose thrust, otherwise it is the other way around. Therefore, let us now try to take a look at some of the results from this expression. All what we did was, this is the value we derived and this is the value we get for the optimum value, I took gamma minus 1 outside over here, and now if I take a look at the optimum value of Cf, which I call as thrust coefficient, that is Cf is thrust coefficient, Cf dot is optimum thrust coefficient. What is it I find? As I increase the value, of Pc by Pe, that means I over here the value is Pe by Pc, that means I have higher expansion ratios, higher value of Pc over here, lower values of Pc over here. As I increase the value of Pc by Pe, I get a higher and higher value of Cf, and the values which are realizable are around 2.4, 2.5, and you find that a lower value of gamma gives me a higher value of Cf than a higher value of gamma. That means the value of the thrust coefficient is sensitive to the value of gamma in addition to being a function of Pc by Pe. The same thing I plot on this particular diagram, wherein I plot the thrust coefficient as a function of gamma. I find that at low value of Pc by Pe, gamma does not influence the thrust coefficient at all, whereas if I have a small value, that means I have Pe by Pc, which is a very small number, the variation in gamma causes a considerable change. That means a decreased value of gamma will give me a higher value of Cf. Therefore, what is it I have done? We looked at the thrust coefficient, optimum thrust when you have the case of P equal to Pc, Cf dot into Pc80, we find that the value of Cf is also a function of gamma in addition to being a function of Pe by Pc. A small value of Pe by Pc or a larger value of chamber pressure gives me a higher thrust coefficient. This gamma depends on this value. If this value is not large, is not small, like for instance I have a low chamber pressure, then gamma is not influential, but otherwise a small value of gamma will give me a higher value of Cf0. Okay. This is all about thrust in a nozzle, and how now what we have done? We have simplified the whole nozzle calculations, and what is it we have done? We told ourselves, well, m dot, the mass flow through a nozzle, is equal to 1 over C star into chamber pressure into throat diameter, where C star was equal to under root RTC by gamma, which we called as characteristic velocity, unit is being meter per second, and we said force in a nozzle is equal to Cf, whether under expanded, optimum or over expanded, is equal to Pc into At. Two simple expressions. Therefore, whenever we make a nozzle, we go and evaluate the nozzle for its C star, but C star does not come from the nozzle. We will see why. Because we are talking of the transfer function between mass flow rate and the chamber pressure, whereas the thrust coefficient tells me what a nozzle is doing. It takes the chamber pressure, multiply by a coefficient, it gives you the force, and that is why we say this is the performance of a nozzle. I think I need to go a little deeper into this particular expression. Therefore, let us write out these two expressions in a slightly different form and dwell on this for maybe next couple of minutes, and with that I think we would have done some justice to the nozzle. But before that, I would like to again emphasize what is it we have done so far. We took a nozzle, we assumed the nozzle is adiabatic, reversible flow, isentropic flow, one dimensional flow. So far it is all one dimensional, and for one dimensional flow we derived all the expressions for Vj, we derived the expression for under expanded, over expanded, maybe flow outside the nozzle and all that, and now we find I can write m dot is equal to 1 over C star into PC80. We also derived the expression for the thrust from basics. We find it is equal to a coefficient into PC into 80. Now, if I play with these two equations, I find over here I find PC80 common. Therefore, can I somehow put this together? Can I substitute PC80 from mass equation into the force equation, and if I were to do it, I get Cf, I get PC80 is equal to m into C star. Therefore, I get here m into C star m dot into C star, and now I get the force thrust developed divided by m dot is equal to Cf into C star. And what is F divided by m dot? What is the thrust per unit mass flow rate? That is, we are talking of F dt impulse divided by mass of the propellant which is there. Impulse per unit mass is specific impulse ISP, or rather what is it we have got? We have got ISP is equal to thrust coefficient into C star. But we had got an expression for ISP earlier. The expression for ISP was Vj. What was Vj? Vj was when the exit pressure was matching the ambient pressure. That is when we derived the expression for, we got the value. Now you have the contribution coming from the exit pressure also, and to some extent what is happening, we never considered flow in a nozzle. Therefore, what is it telling you? It is telling you ISP depends on the performance of the chamber. And what does the chamber do? Chamber in generating or producing high pressure. And what does Cf do? Cf is in the nozzle, which converts this high pressure into high velocity, or the nozzle effectiveness, or the nozzle's role, and therefore Cf is a figure of merit of the nozzle, how it converts the high pressure into velocity, and C star is a figure of merit of the chamber, in that it will tell you how high pressure is generated in the nozzle because of some mass flow rate. Therefore, you have a composite index. Therefore, ISP is a product of pressure generating capacity in the rocket. And how is pressure generated? Through C star, whereas once the pressure is generated, the nozzle helps you to generate the high velocity, high jet velocity. Therefore, you have both the chamber capacity, that is a propellant to generate hot gases, and Cf, which means the effectiveness of the nozzle. Therefore, ISP is equal to Cf plus C star. But you know what we have done so far is all ideal, one dimensional and all that. Therefore, it is necessary for me to go back and ask myself, is everything cannot be ideal. Therefore, there has to be something like some efficiencies, and therefore, can I talk in terms of efficiencies for mass generation and efficiencies for thrust. The mass generation we decided in terms of C star. Therefore, if I have to put an efficiency for mass generation, it is equal to C star, which is experimentally observed, divided by the ideal value which we derived in this class. And what was the ideal value? Under root RTC by capital gamma, and this is where. Therefore, all what we do in an experiment, you take a rocket, you find out what is the rate at which mass is getting delivered out, you find out the ideal and you say it is eta C star, and you will find that the values are quite high, of the order of 0.98 to 0.99. We will do some problems on this. How do you get the thrust value, efficiency for thrust? You call it as thrust correction factor. And you denote it by zeta f. correction factor which is equal to, we say, Cf actually measured in a chamber divided by Cf whatever we calculated was ideal, and we use the ideal value to find out the efficiency, and again these efficiencies are quite large for nozzles of the order of again 0.98, 0.97 and so on. Therefore, what we have done in today's class is we looked at the high temperature and high pressure gases generated by the propellant. We expressed it in terms of C star. That means C star tells you what is the rate at which hot gases gets generated from the propellant, and therefore we wrote it as m dot is equal to 1 over C star into Pc AT, where Pc is the chamber. We called it as a transfer function, and the expression for this was extremely simple, is equal to R Tc by the particular value of gamma. We also talked in terms of the thrust coefficient which is used to generate or describe the thrust developed by a rocket. F is equal to Pc AT, and we found out the expression for Cf and also how Cf varies, and we talked in terms of a thrust correction factor which is equal to Cf actual by Cf which is calculated based on ideal one dimensional theory. Now, sometimes an effective jet velocity is defined in the literature to determine the composite of the jet or the velocity thrust or the momentum thrust and the pressure thrust. Let us examine what this effective jet velocity is. Let us say that the total thrust is given by the momentum thrust which is equal to m dot into Vj, and the pressure thrust is because at the nozzle exit the pressure Pe is greater than Pa and into Ae, this becomes the pressure thrust. Now, if I have to put this thrust in terms of an effective jet velocity, I say F is equal to m dot into V effective, and this is equal to m dot into Vj plus you have the same thing Pe minus Pa into area, and therefore the effective jet velocity is equal to the jet velocity plus you have Pe minus Pa divided by m dot into Ae, and this is defined as the effective jet velocity. And when a nozzle is not adapted, that means the exit pressure is different from its ambient pressure at that particular altitude, well, the effective jet velocity is different from the jet velocity at the exit of the nozzle. This is to take care of the pressure thrust in addition to the momentum thrust over here. We continue with nozzles in the next class, but in the next class we will try to take a look how do I contour a nozzle and what are the approximations from the ideal cases what I have studied, and this is what I will do in the next class. Well, thank you then, I think that is about it.